Hi everybody, I am back. Alright, so I just had a quick look over things there. So I can say, it would be very much in your interest to practice more questions on TCP. The You might want to look at, particularly, you might want to look at, first of all, can anyone hear me? Am I just talking to the wall? Yeah, yeah. So you might want to look at the uh, the the multiplicative increase and the how TCP switches from that really fast start situation over to the linear increase. There was some detail in the lectures on how that actually happens with various thresholds, etc. So, I would advise going back over that earlier part, or that part at least of the TCP lectures. Um, okay, I'll say no more. Right, so let's move on to maybe the last part of the course, section 6. So let's see what I have in the exam paper that's actually open at the moment. So January 19. Yeah, okay. So consider an internet address of this form here, 128.129.40.23. What does the backslash 23 represent? So that's your subnet prefix. So that means that the first 23 bits of the 32-bit IP version 4 IP address are fixed for that particular local area network, or subnet, whatever you want to call it. So for that particular subnet, the first 23 bits are set, giving you 9 bits that can vary. So for this case, only 9 bits in the subnet can vary, which means how many IP addresses could there exist on that subnet with this prefix? Nine bits, 2 to the power 9 gives me 512 possible IP addresses. Okay, let's see what the question is. Consider the network above. So you can see the network, right? You've got 3 subnets, 15 hosts here, 12 here, 45 over here. How do I know they're subnets? You remember the rule we had? If you go to your routers and your hosts and just disconnect the interfaces, what's left tied together? So you can see, just disconnect these interfaces from the router and you'll be left with these islands of IP addresses. Consider the network above consisting of OR1 and those 3 subnets. Assign an IP address range to the hosts such that only a single aggregated address need to be advertised by OR1 to the public internet, and the size of the aggregated address ranges that is advertised is minimized. In a sentence or two, explain how you arrived at that answer. So you can imagine here OR1 wants just to send a single single subnet prefix that will account for all of these 3 cases here. What's the smallest one it can do? So let's just consider each of the 3 subnets one by one. So I'll copy this into my lightboard, or my whiteboard. Alright, let's start off with subnet A, 15 hosts. So with 15 hosts, how many IP addresses am I going to need? I need a minimum of 15, but with 2 bits, so I need, oh, that's way too big. So 15 hosts. Remember, I have to use binary system here for my numbers, so that means that I'm going to have to use, so remember what the number of bits, so if I use 3 bits, 3 bits will get me 8 addresses. So I'm going to have to use 4 bits here. Equal to 16 addresses. So I'm going to need 4 bits. So let's call the IP address here xxx dot y dot z. I've run out of letters. Let's just call it xxx dot xxx dot xxx dot xxx backslash. So we're going to say that the first 32 minus 4, 28 bits are going to be fixed here. So the 28 would be the subnet for this particular case here. So that means I can allow these 3 bits here, these 3 bits, or these 4 bits here to change. What about over here for the 12-bit case? Same story for the 12-bit. I'm going to need another 4 bits here because it's 12. So same for this guy here. Same story here. For the 45, I'm going to need to increase it, right? So I'm going to need 6 bits here to get me up to a 64. Now note that 1 is wasted here. One address is wasted. Note that here I'll have 4 addresses wasted. Using 4 bits. Here, for this one, I need to use, I need 64, right? So that's going to bring me up to 6 bits. I need 6 bits to adequately represent 45 addresses, but I'm going to be wasting 19 of them. So let's go through that. So for A, I'm going to need something like this. Well, let's go through the A, B, and C here. What would the address spaces look like? Did I give a number to start to use? No, I didn't give any number. Okay, so let's just go something like this. So x dot xxx dot x, and now I need to put in a 0 or a 1 here. So if I put in a 0 here, and then these guys can be anything I want. That'll cover A. xxx dot xxx dot xx, and then a 1, and asterisk here. That'll cover. Am I right? No, that's not right. Sorry, that should be an asterisk there as well. Hold on. Okay, so you can see I've got 4 bits that can change here for A and B.
How do you decide if it's going to be a 0 or a 1?
Well, if it was If it was exactly the same, right? So imagine it was exactly the same here. Let's just say I got rid of the 0 and the 1. I just put in my x here. I've got the same numbers. I've got the same values here. Maybe I'll just put in the actual values here, ones. Sorry, I'm actually making a mess of this with the decimal system as well. Let me just rub it out and be a bit clearer. Yeah, the best way to write this. Okay, the easiest way to write this is I'll just do a big X dot Y dot Z, and I just write out the last byte here in ones and zeros, if that's okay, and then it'll be a little bit easier to understand. So let's put down a 0, 0, 0, and now I need 5 bits here. So it'll have to be a 0 and a 1, a 0, and then these guys can change. The last 4 bits are going to change. And then for the next guy, it'd be X, Y, Z, 0, 0, 0, 1. So your question was, how do I choose to put down a 1? Well, if I didn't put down a 1 there, if I left it at 0, it would be exactly the same address range for A and B, which doesn't make sense. It has to be different. Hence the 1 will give me a different set of addresses for these last 4 bits. Does that make sense?
You say swap the 1 and the 0, so put 1 in A and a 0.
Oh yeah, absolutely, yeah. As long as they're different. It's up to you how you assign your addresses within your subnet. So what about C? Now C is a bit different. So C is going to be X, Y, Z. You're told I need 6 bits here, so it's going to be 0, 0, 0, 0 would be okay, but then I need these 6 bits here. Now here comes the problem. You can see I'm using up an address range here for this address range is covering these two address ranges up here. So I have a problem. So I need to put a 1. I need to put a 1 here. I need to put a 1 there to differentiate it from these guys. Okay. Now there's a bunch of wasted addresses here. You can see I've still got loads of addresses I can use that haven't been used here. There's tons of them that haven't been used here, and I can still use them. But this is pretty much the minimum I can advertise if I'm going to have independent subnets here. So what R1 would advertise to the rest of the internet would be, so R1 would advertise x.y.z dot 0, 0, 0, 0, 0, 0, whatever, backslash the first so the only things that don't change here is everything before here. So the first 32 minus 7, so 25 bits, backslash 25. So that's what R1 would advertise to the rest of the internet, and it would cover these 3 different address ranges here. Now you could probably do a little bit better than that, but that's a good answer. You could also use this address range to give a lot more. Like I haven't used all the addresses here at all. You know, these zeros haven't been used at all here. So anyway, let's move on. Part B. Consider the network shown above. Oh, that's done. Part C. Assign a specific address range and MAC address to the host shown in subnet A. Okay. Same for the one in subnet C. And give an IP address to the router interfaces as well. Alright. So alright, so I was asked to do an IP address for this guy here on the left, subnet A. So let's do that. So I can use all zeros, is fine. So x dot y dot z dot zeros. And the router here, remember the router here has an interface, has an IP address at this interface as well, and it should belong to the same subnet, so it's on A. This is part of subnet A. So if I go back up to my address range, I'm allowed to use some space inside here. So I've just used 0000 for my first one, but I can use 0001 here. So x dot y dot z dot 00000001, and that's fine. They're clearly part of the same subnet. What about this one over here? For C, let's do C now. C is I use this space here, xyz.01, so x.y.z.01, and now I can just use anything I want, so I'll go with 00001. And the router here, same story, has to belong to the same subnet. Remember the address range is up here, so x.y.z and then I'll go 0100 and then 0000. I could have used 0 down here. I'll use I put 1 here instead. Okay, so they're clearly part of the same subnet space. Okay, so that answers that. The MAC address is random. You know, you just choose your MAC address to be whatever, a.bb.cc.dd, whatever, .ee. Yeah, and the same story down here. Whatever you want, just call it, or you know, just use a whatever, just random values. You know, if you want to just do it quickly, I often do it for something like this. If I want to write down something that I can use again, I will just either write down Mac1, Mac2, or if you want to be a little bit more correct, you could do something like a.b or a b b b b b b b b b b, and then C C C C C C C C C C C C C and D D. They're all valid digits that would be used in hex. So they're all valid MAC addresses. But you could easily just write out Mac 1, Mac 2, Mac 3, Mac 4. I'd be happy enough. What are the source and destination? Okay. Consider an IP packet. So the next part of the question was, I'll switch over. Consider an IP packet sent from the host in subnet A that is destined to the host in subnet C. This IP datagram is contained. Okay, so this is where you should really listen up, because this is something that seems to, I seem to put this up in nearly every question 6, something like this. So consider an IP packet sent from the host in subnet A. It's destined for the one in C. The IP datagram is contained inside an Ethernet frame, obviously, and sent from the host in C to the router at R1. What are the source and destination MAC addresses of this Ethernet frame? What is the source and destination IP address? The IP, yeah. So let's go through that. I mean, it's pretty straightforward, really. You just have to get the idea, and then the whole thing kind of makes sense. Okay, so we're going to look at the Ethernet frame being sent. I'm going to just do it right here. Okay, so imagine we're sending a datagram here from A to this one down here, right? So from subnet from this guy here, we're sending a datagram to this guy down here. All right. So what's the datagram going to look like? So let's pick out a point here. So it's being sent first inside an Ethernet frame to this router interface down here. So it's being sent from here to here. What is that Ethernet frame going to look like? So we're going to have, this is an Ethernet frame. And we're going to have a source and destination IP address here, or sorry, a MAC address. And here, so this is our source and destination, and inside here, of course, we've got our datagram buried inside. is our datagram, and it will have a source and destination IP address. So what will that look like in this situation? Does anyone want to tell me what's going to be in here? So this is our source, this is our destination, a MAC address, and here's our source and destination IP address inside the datagram. Anyone? Deathly silence. Okay, so this, you should be kind of getting this at this stage. So the source and destination MAC address are simply the source MAC address here, AAA, here, right? So let's put that one in, AA.AA, etc. The destination is going to be the interface destination for R1, not the MAC address of the final destination. The MAC address of the interface at R1 that it's sending it to. So it's actually going to be BB here. Okay. Meanwhile, the IP datagram that's buried inside that Ethernet frame will have the actual source and destination IP addresses that are the true source and final destination. So that'll continue to be whatever. What have I got down? X, Y, dot, Z, dot, zeros all the way across. So that's just the IP address of A over here on the left. The destination will of course be this one here. So it'll be this IP address here. So it'll be xy.z.0100000000, whatever. And that's what the MAC address will look like there. Now what happens inside the router? So once that's received inside the router will demux. So it'll pull out all of it'll get rid of all this Ethernet frame. Just takes out the datagram that's buried inside it. It looks at the destination IP address, and that's when all that routing will happen. You know, your BGP and your link state and whatever else, whatever needs to happen, that'll all happen now, and it'll decide that it's going to send it on this link over here. That this is the best link to send it on its journey. And so what happens next? What is the Ethernet frame going to look like now as it gets from here over to here? What is this Ethernet frame going to look like? So our datagram is still our datagram. It's now just going to be buried inside a different Ethernet frame here. So now what is the source and destination MAC address? Anybody? No? Okay. Am I on my own here, or is there anyone still there?
Is this part for when it sends it from R1?
Yeah.
So would the first would be the DDDD?
The source, so remember, is that what I called it? Was it? No, the if you see this arrow here that I have here, that's pointing to the addresses for R1 here. So the source would be from R1. I think, yeah, no, I think you've got the right answer. You're just looking at the wrong point. So the answer is, yeah, you're sending it from the MAC address of this interface, which was CCCCC. So that's the source.
And then the destination
would be DDD, yeah.
So did you need like 2 Ethernet frame diagrams for this concept?
Yeah, ideally, you know, I mean, I just did it with one there because I was able to rub out the thing. But if you wanted to do it really quick, and sometimes people answer this question because I ask this type of question so often. People would just write down like just to save them time. They'll often write down something like this just for the address space. They won't even bother adhering to their earlier answer. They'll just write down IP1. IP1 MAC1, IP2 MAC2. I don't like this type. At least there should at least be an obvious relationship between IP2 and IP1 in the same subnet. If you know what I mean. It'd be nice to see the bits being related to each other on the subnet for the IP address, but it's okay. This is an okay answer as well. So it just is a bit quicker to do it this way. So and then I'd have here IP3 MAC3, and then here IP4, MAC4. And then you can just do it very very quickly with your fields. It's just like Mac1 to Mac2 first, and then for the second Ethernet frame, it's going to be Mac3 to Mac4. You know what I mean? And then inside you've just got the datagram, which always has the same. It never changes.
The max, they're completely arbitrary, but when you're doing this out for the IPs, try and keep them consistent.
Yeah, that's what I mean. At least if you do that, it demonstrates to me that you understand that IP addresses are hierarchical, whereas MAC addresses are flat. MAC addresses have no useful information in them, whereas IP addresses do. I can identify that two hosts are in the same subnet by looking at their IP addresses. You couldn't possibly do that with MAC addresses.
Okay. Yeah.
So that's a faster way of answering it there. That's obviously the first Ethernet frame over on this side, and this is the second one on this side. Okay. What's the last part? Now consider the Ethernet frame carrying this. What are the sources? Okay, I've answered it already. Okay, that's that question finished. So this stuff is easy enough on the MAC address side. If you just get what I've just done now, a lot of the time you can answer a big part of the question that I do for question 6. Because it's trying to show you or get you to understand the relationship between MAC addresses and IP addresses, how they're different. They're both used by their different layers, obviously, but and they both are similar in many ways, but there's fundamental differences there too. Also, this forces you to get your head around the idea of encapsulation across the different layers. The link, like an Ethernet frame will only exist on one link, and then it gets demuxed. The datagram gets pulled out, and it's no longer on that link, and then it moves on to the next link, and whatever the link protocol for that new link is, will determine what kind of frame will carry it. It could be a Wi-Fi frame, or an Ethernet frame, or it could be a fiber frame. It doesn't really matter. And they all have different rules, of course, these different link layer protocols. I didn't really get to cover Wi-Fi properly. I did before in a previous year, but this year we really had to streamline the course a little bit, so I'm not doing any Wi-Fi this year. But the yeah.
In that scenario, so the datagram first of all goes to OR1 with source and with it being the destination. How does it know the destination for the second Ethernet frame going to the final point at MAC4?
Yeah.
Does it know because it knows where IP4 maps to?
Well, that's a great question, and that's the kind of question that I would be able to answer for the exam. So that question is like, so what he asked there was, how does R1 know what MAC4 is, or where MAC4 is. So let's go back to what happens there. So the very first, so the IP1 there and IP2. Okay, we've done that bit. So we've got this first frame here, Mac1. I'll just point to it here so you know what I'm saying. You've got this guy arriving to the router, right? And once it arrives to the router, the datagram gets pulled out. So we just forget all about this Mac1 and Mac2. It's no longer interesting. It's gone. It's yesterday's news, if you like. We move on to the next link. So now we've got this datagram. So the router has to decide what to do next. So the first thing that happens is routing. So it looks at IP4, the IP address 4, and it says, where is that? What link? What output link should I use to send that on? Will I send it on to subnet B, for example, or will I send it to subnet C, or will I send it into the general internet? So it has to make that decision, and how does it make that decision? It uses the network layer protocols with this data. The protocols that work with IP addresses. Those are the protocols that you learned about, the algorithms you learned about, those link state, that distance vector one, and of course BGP, the big one that ties everything together. Those are the protocols it turns to, and then after doing some calculation, it decides, oh, the best route, the best one to send it on is this link over here to subnet C. So it makes that decision. It forwards it on to that output link then. So that's the first thing that happens, is routing, and that's all done at the network there. I didn't mean to do that. Yeah. That all happens here. Okay, so that happens at the network layer. Nothing to do with Ethernet at all at that point. But now we've made the decision to push it onto that link. What happens next? And your question was, how does it know where to send it to? And of course, there must exist. So once we go down to the Ethernet layer, IP addresses don't really mean anything anymore, right? We're just looking for the MAC address of our destination. But then we need to be able to link our IP address to that MAC address in order to figure out where to send it to. So how do we do that? How do we map between? So we know we want to send it to IP4. So you can imagine the router here at this point. It has this IP datagram. It's decided it wants to send it out on this link here. And it starts to make this frame over here. So it knows its own MAC address, obviously. But how does it figure out what MAC address to put in here? That was the question. Anyone? You got to know this one. How does it figure out what MAC address to put it in here? To put in here as the destination. Well, we had a lab on this, guys. You should be shouting the answer out. So the answer is ARP. So with ARP, the answer is you don't normally know. You don't necessarily know, in general, what the MAC address is. So R1 shouts out, if you like, to everyone, broadcasts to everyone on the network, sends an ARP message. So it shouts out to everybody who's got IP version 4, IP4, not IP version 4, IP4 address. Who's got address IP4? And that gets sent to everybody. So every single host on the entire subnet C will receive that ARP query. And everybody will ignore it because obviously they don't have IP4 address or the address IP4, except for one guy here, this one. And it'll realize, hold on, someone's just asked for my MAC address, so it'll reply with an ARP response containing the MAC address for containing the MAC address for this host. And then once R1 receives it, it can now write in, oh, that's MAC4, I've got it. That's the one that corresponds to IP4, and then it'll save it in its table, its ARP table, for some period of time, up to like 20 seconds or something like that. Some time to live. Does that answer your question?
Yeah, that makes sense. Thank you.
So the answer was ARP. So you should know that one. The other thing you might want to know at this point is the switches. Do you remember the switches? I did a video. I'm not sure if you've watched it yet. I did a video on how switches work. So the reason why ARP will only save the MAC address, the IP MAC mapping for 20 seconds or so, is because those mappings can change from time to time, because the IP addresses are leased out via DHCP. So with those MAC addresses linking to temporary IP addresses, it's necessary to ignore those mappings from time to time. That's one thing to remember as well. Another thing is the we haven't talked about switches here. So switches they're like routers. Let's see if I have any question on switches. Actually, it might be nice to cover that. Can I delete that? Delete. Yeah. I'm not sure if I have actually. Let's see. No, I'm pretty sure I don't. But you might want to look over your switches, how the switches work. I did a really nice graphic on the slides, if you go back over the videos on switches, to show you exactly how switches figure out what to do. So with switches are a little bit different. I'll just maybe do a quick representation here. So the difference between a switch and a router, I've drawn 6 switches here. The difference between a switch and a router, first of all, there's several similarities. They both receive a packet and forward a packet onto a link, an appropriate link, not necessarily all the links, unless it's ARP or something that's been broadcast to all the links. So a switch will select the best output link to use, just like a router will do, and it'll forward the packet onto that link. In this case, it's an Ethernet packet as opposed to a datagram for the case of routers. So let's go through how these work. So imagine we've got, say, a number of different links here. So we'll say we've got M1 here, we've got M2, we've got a link to here, say M3, M4, M5, M6, M7, M8. So we'll imagine we've got a hierarchy like this. And this is the kind of thing that will happen in the university, for example. We'll have these really high-speed switches connecting our Ethernet cables together and connecting all of our different hosts together. When, for example, we'll call it M1 here, sends an Ethernet frame destined for, say, M8 over here. How does it figure out where M8 is? How does it know which links to use? That's the question here. So this is switches. And the answer is it figures it out dynamically. So it's a plug and play method. So it'll figure it all out by itself. Nobody has to come in and tell it which link to use. You can imagine that would be a nightmare for a system administrator to tell M1, okay, use this link here, link 1, use link 2. So I'll actually number the links here as well. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So nobody is going to come in and say, okay, if M1 wants to send a Mac, wants to send an Ethernet frame to M8 over there, you should use link 1, then link 3, then link 7, then link 8, then link 13. You know, nobody's going to configure that. It has to figure it out itself. So switches do that themselves using a very simple approach. So the switch actually has its own table inside it. A little bit like your forwarding table with the network layer for routers that routers use. A little bit like that. So the switch it'll learn and remember where different MAC addresses are on the system, and then it'll put them into its forwarding table. So let's see what would happen now, for example, if M1 wanted to send a frame to M8 and then M8 wanted to send one back. What would happen? So we'll imagine the switches know nothing, so they're completely empty. They've learned nothing yet. So what happens first is M1 sends the frame to, so here comes the frame here. It's got M1 to M8 on it. So it arrives over here. What happens next? So the switch doesn't know where M8 is. It has no idea. It doesn't know where anything is yet. It hasn't learned anything yet. So it sends the frame everywhere. So it sends this frame we've just created here. It sends it this way onto link 3, and it also sends it down to link 2. All right. Now you can imagine when M2 receives it, it goes, that's not from me. It's got nothing to do with me. I'm not M8, so it drops it. So it's gone down here. Never climbs up the stack on that host. Just gets dropped at the link layer level. Meanwhile, this one's gone on up here to this switch up here. The switch doesn't know where anything is either, so it sends it everywhere. So now we have our frame going this way and down here as well. Now let's follow this one down here first. So this will arrive at this switch down here, and it doesn't know where anything is, so it'll send it down here and down here. M3 and M4 will realize it's not for them, and they'll just drop it. There'll be no reply. Now, actually, what I didn't show you there, I should have showed you there, is the tables at each one of these switches. So this switch here when it received that frame from M1, it took a little note. It said, look, I know now M1 is reachable from link 1. So it takes a little note. Same thing up here. When this switch received the frame here, it made a little table here. It said M1, because that was the source address, M1 is reachable on link 3, because that's the link it came on. Same with this link down here. When it received the frame, it said, look, M1 was reachable on link 4, because the source address was M1 and it came from M4. It came from link 4. And so on we go. Now the frame arrives over here at this switch, doesn't know anything, so it sends it to everybody. So it goes down here. It goes down here now, gets pushed down on 8 and on 9, all the output links. Doesn't send it backwards, never sends it backwards. And of course the table here updates as well. It says, okay, now I know that M1, the source address in the frame, is reachable on link 7, the link it came on. Same story. Now, meanwhile, the frame goes down here on 8 and 9. 9, once again, it'll reach here, and we'll make a little note, M1 was reachable on link 9. And it'll get down all the way to all the way down here to M6 and M7, who'll quickly realize that frame is not for them. They'll just drop it. No reply. Meanwhile, here comes the frame down here on link 8 down to this final switch. And it'll get pushed on here and pushed over here as well. Now, of course, once it reaches this switch, it'll realize M1 was reachable via link 8, the link it just came on. Now, when it reaches 7, it's just going to get dropped. But when it reaches M8, it'll realize, okay, this is actually for me. And it'll probably formulate a response. So here comes the response. I'll use a different color here. I see, purple. Yeah, okay, purple. No, I'll go. I'll try this one. Okay, so now M8 is going to formulate a response, and it's going to send something back. So here comes a new frame coming back. Oops. Here goes my new frame. It's coming from M8, destined for M1, and it's going this way. Now, once it reaches this switch here, what's the switch going to do? The switch is going to, well, first thing it's going to record, oh look, M8 has just sent something on link 13. So now I know that M8 is reachable on link 13. Is it going to send that frame down to M7 down here? The answer is no. It knows that M1, the destination here, is reachable on link 8. So it sends it directly here, up to here. Once it's received by this switch, here it's going to record, oh hold on, this is coming from M8. I know M8 is now reachable on link 8. And of course, will it send it down to 9 and then which further propagate on to 10 and 11? No, it won't, because it knows that M1, the destination, is reachable on link 7, so it'll send straight away over here. And then, of course, same story with the next switches. M8 will just get recorded here, reachable via link 7. That'll get sent only on link 3 because we know where M1 is now. And then that'll finally get sent down here to M1. And of course, each time we're just noting where M8 was as we go to the switches. So that's how the switches remember. And they store those mappings. Again, they only store them for a finite period of time, but because you can plug out different hosts and move around to different points on the network, so you don't want to necessarily store these things indefinitely. But that's how it works. So this is just another, if you like, layer on top of ARP. So with ARP, this is yeah, for the purpose of all the Ethernet discussion, etc., you can ignore that these switches exist. You can just imagine that they're invisible. If you want to connect to M1, it just goes straight to M8. Most of my discussion in the lectures is like that. I pretend that these switches don't exist. The switches are just really, really, really high speed devices that can do this really quickly. So they're sort of transparent, if you like. You can't see that they're there. They're so fast. Anyone have any questions about that?
Say if M1 moved before M8 responded, or while the table still existed, would it just not receive any messages sent to it then, or would it be recorded as a new node? Or
Yeah, so the first thing there is, it's very unlikely that that would happen. These switches are so high speed. Well, no, it is possible that it would have a recording of a particular node being reachable, and then that node is just pulled out. Yeah, it could have that. It could have that stored. Um, and then, of course, if it was sent there would just be no response. It would just disappear. If that link,
okay,
if the
so
link
it
was,
just wouldn't reach it.
yeah, you just wouldn't get there. I mean, the message would arrive at that link, and there'd be nothing there to receive it.
Okay, yeah.
Yeah.
That's what I was wondering. Thanks.
Yeah, and then of course, it won't know that that's happened. It can't. The switches can't know that that's happened. They just do what they're told. They just send these messages on these links that are in the tables. But remember, these are stored for a finite amount of time, so that problem is solved by a temporary time to live. And so I think it's not that long either. It's in the order of seconds. So they only remember these positions in the order of seconds, and then they forget them.
Okay, yeah. Thank you.
Yes, that solves that problem. Okay, so I've given you some good stuff there, I think, for studying overall over the last whatever, hour and a half, 2 hours. So I think I haven't bothered going over link state or distance vector for good reason. So I would advise you to study your BGP and how that works. I'm not going to go through any exam questions because I don't have any to show you. You'll be the first. So, but I would just study how it works. It's not that bad. The questions shouldn't be that bad. And I think I will leave it there, guys. So I'll post these 2 recordings. Oh God, I hope I recorded this. Just double check. Yeah, I recorded this. Yeah, so I'll post this since there are only, I don't know, 14 of you, amazingly, in the room. I'll post it, and anyone else that missed it, I suppose, can watch it, or you can watch it back yourselves. Does anyone want to ask me any other questions while you've got me? You've got me for another 5 minutes here.
Yeah, thank you for that. Anyway.
You're well prepared. That's it. You're all so well prepared for the exam. You've got no questions at all. Okay. Yep. Yep.
How long do we have to upload our PDF after the exam?
I've put down 30 minutes.
Okay, perfect.
Yeah, the department haven't issued me with any instructions yet, the CS department, but it's not my first time doing this now, so I think 30 minutes is fair. A fair amount of time. You just have to.
That's kind of what we've got across the other modules as well.
Is it? Yeah, yeah.
Standard now.
Yeah, I gave an hour last year, and it was a bit of a disaster. But I think half an hour is reasonable, and the EE guys are making me do 15 minutes, which seems a bit unfair. 15 minutes isn't very long. But I mean, if they're late coming in, I mean, people are gonna no doubt. I've got 100 in the class, even if only 14 of you show up. But there's no doubt going to be network issues somewhere for someone. So I mean, it's not uncommon that someone will have to send it in a bit late or whatever. And you can always use email as well. Email is quite effective. And if you've got your smartphones, you should be able to scan with your phones and send. So it's unlikely your 4G will go down. So hopefully that'll work for you. If you have a decent if you have a decent phone reception. And if you don't have decent phone reception, you should probably go somewhere where you do, if you can. Although I know moving around at the moment isn't exactly easy. Yeah. Look, we're fairly understanding. Let's put it that way.
And can I ask a question?
Yep.
You know the lab quizzes you've done, will they be available for review?
Oh yes, yes, they are. They should be available. Do you know what? I'll do that right now. I ran very generously. I ran the labs again for anyone that missed them there because there's a lot of people missing them. So I didn't want to open them up. I'll post. I'll open them up now, so you can see them, and I'll also publish your CA grades. I will note that every year people come back saying I wrote down 9 in capital letters and I wouldn't give me any marks for it and whatever. To accommodate for all those kinds of little problems, I add on 5% to everybody's grade at the end. So please, I know there's little bugs out there, but don't bother sending me 100 emails. I don't have time to answer all the emails, unfortunately. So just take it that I am adding on 5% as a to everybody's grade to account for that, and anyone that goes over 100%, as has happened on occasion, will be capped at 100%. Okay, so yeah, so I'll open that up, and I'll do that. I'm just going to I have a meeting now, but after I have that meeting, I'll do that. Okay. Okay, guys. I might post out some feedback as well, forms for just getting feedback from the course. If anyone has any constructive criticism or nice things to say, even I don't mind. If you want to say something that you think might help me improve the course. I know it was a tough year, but I'm open to any suggestions you have at all. Okay, guys. I'll leave it there.
Thank you.
Take care. Good luck in your exams.
Thanks a million. That was great.
Take care now. Bye bye.